Okay, the Lagrange inversion formula takes a bit of setup to state. Let f be analytic around 0. So when I say around 0 or at 0, it just means it's analytic on a disk centered at 0. And so you could get to this case by translating. And we'll also assume that f maps 0 to 0. Again, you could translate in the range to arrange for this. And we'll assume that the derivative is non-zero at 0. So by the inverse function theorem for analytic functions, f is locally analytically invertible. And so the question here is, can we give a formula for the coefficients of the power series of f inverse centered at 0? So step one is to kind of rewrite f a little bit. Step one is to write our function f in this form as z divided by phi of z, where phi is some analytic function which is non-zero at 0 and defined near 0. So you might have to shrink your domain a little bit to arrange for this, but you can. So how do we come up with phi? Well, f is equal to a power series near 0 with a0 equal to 0 and a1 non-zero. So then you can divide through by z and you still get a power series here, which is perfectly analytic, and it turns out to be non-vanishing at 0 because its value at 0 is a1. Okay, so now this is analytic and non-vanishing at 0, so 1 over it will be holomorphic still, and we prove that holomorphic means the same thing as analytic. So this function, which is what phi is analytic and non-vanishing at 0. So you just have to kind of arrange f in this manner. But we do need to point out that phi itself will have its own power series, and the Lagrange inversion formula will involve the power series of phi, which you could get from the power series of f. Okay, so here's the statement of the theorem. This is really, maybe calling these steps is an exaggeration, but let's write out some notation for the coefficients of f inverse. Then the Lagrange inversion formula says that Bn is 1 over n times the coefficient of z to the n minus 1 in the power series for phi to the n. And you can compute this from our Cauchy integral formulas. The coefficient of, if I just had, say, f of w, and I wanted its nth coefficient, we did that by integrating w to the n plus 1 dw 2 pi I on a circle around 0. And so here we want an n minus first coefficient, so I'll just have an n here, so this would give me an n minus first coefficient, and the function I'm using is phi to the n, so you can write the formula like this, where r is just sufficiently small. So this is the formula, and it turns out to be too hard to prove right now. We're going to have some more techniques that'll make this easy to prove, but I think it's easy to look at some examples of this for computing the coefficients of an inverse function. So first, let's look at some examples that are rigged to have a nice phi in them in the setup from before. So if I take my formula here, let me put both steps here. Let's look at f of z is z over 1 plus z squared. And so it's already arranged in the right way. I can take phi to be 1 plus z squared. And then the formula over here tells me to compute the coefficient of z to the n minus 1 in the power series for phi to the n, which in this case is just 1 plus z. to the 2n. So we'll just have to extract a binomial coefficient of 2n, choose n minus 1. So f inverse has coefficients bn, where its nth coefficient is 1 over n, we can't forget that part, times this binomial coefficient, which you can rewrite this way. And in this simple case, we can actually solve for f inverse in a certain sense in terms of other analytic functions. We know you can't always do that, so that's one reason why the inverse function theorem is of theoretical importance, because you won't always be able to do this explicitly. But in this case, you would do what you learned in middle school or high school and switch the variables and solve for w. And you get that w is some expression involving a square root. You have to choose the right branch here in order to assure that this will be analytic at 0. See right here, we would choose the branch of square root so that square root of 1 is 1 and not minus 1. And we can form a local branch of square root near 1 to take the square root of 1 minus 4z here. And we want it to be the one in this formula because we need the top to vanish at 0 so that some z's will cancel in some power series. I don't want to go through all those details right now, but the point is you'll get a power series representation for this function, which is essentially closely related to this square root function. And so we've found its coefficients through the Lagrange inversion formula. The next example is this function we had from before. F of z is z over e to the z. Let me move my steps over here. So again, this is written conveniently so that phi is very easy to recognize and compute its power series coefficients. So now we need the n minus first power series coefficient of phi to the n, which happens to be e to the nz. Well, the nice thing about that is that I just have to put the power series for e to the z and then put nz into it. And so then the coefficient of z to the n minus 1 would correspond to k equals n minus 1 here. And so you'd get n to the n minus 1 over n minus 1 factorial. And in the formula, we do have to do a 1 over n. And we get the power series representation of the local inverse of f right here. And so it has these coefficients. And I believe for a homework problem earlier, we computed that the radius of convergence of this power series, or else the one closely related to it, was actually 1 over e. And 1 over e corresponds to the point f of 1 equals 1 over e. So this inverse function is analytic all the way up to kind of the bad point that we discovered earlier when we took the derivative of this function to be 1 minus z over e to the z. So there's something bad that happens at 1. And so we can't go past 1 even in our power series formula. Next, let's briefly talk about the implicit function theorem for analytic functions.